In this video, we pay attention to the triangle inequality in L2 norm spaces. Let U1 and U2 belong to the L2 functional space. Then you have that the L2 norm of U1 plus U2 is bounded by the L2 norm of U1 plus the L2 norm of U2. It's a really important result in functional analysis to obtain appropriate bounds. We would go through the proof now. We take U1 plus U2, we take the L2 norm squared. This is by definition the integral U1 plus U2 squared d omega. U1 and U2 are real valued functions, okay? So from here, we just expand the bracket. So it's U1 squared plus 2U1 U2 plus U2 squared d omega. We can split the integrals here. So it's the integral over omega U1 squared d omega plus 2 integral over omega U1 U2 d omega plus the integral over omega U2 squared d omega. This is the L2 U1, the L2 norm squared plus 2, we rewrite this integral, and this last integral is the L2 norm of U2 squared. We can bound this bit here. So this term can be bounded using Cauchy-Schwarz inequality. So we can bound this term here. So it's the norm of U1 L2 times the norm of U2 in L2 plus the last term here, which is U2 L2 squared. Of course, this can be written as U1 norm of U1 squared. Sorry, this can be written as norm of U1 plus norm of U2 squared. And the next step is the following. So we have that U1 plus U2, this norm squared, is bounded by the norm of U1 in L2 plus the norm of U2 in L2 squared. So from here, we have U1 plus U2 in L2 squared, and then we raise to the power of 1 divided by 2. And we write the right-hand side by taking the square root. This is squared, and this is 1 divided by 2. From here we have U1 plus U2 in L2 bounded by the norm of U1 in L2 plus the norm of U2 in L2. So this is my result here. And this concludes the proof. This is the triangle inequality. for L2 normed spaces.